In this video, we're going to talk about approximating areas under curves using rectangles. So we're just going to launch in with an example. Let's say we want to approximate the area under the curve y equals x squared, which is sort of a boring function, from x equals 1 to x equals 3. So here I've sketched the curve y equals x squared, and I want to know what's the area sort of between this value of 1 and this value of 3. In order to approximate this, we're going to use rectangles. Why are we using rectangles, you say? Those might give us sort of lousy approximation. This looks a lot like a trapezoid. Why not use a trapezoid to approximate it? And the answer is, well, our selection is somewhat arbitrary, that you could use whatever type of shape that you wanted to. The reason why we end up using rectangles is twofold. One, it's really easy to compute the area of a rectangle, right? It's just base times height. And it turns out it's not going to matter that rectangles end up being a lousy approximation in this case, because we're going to show that using lots and lots of rectangles gives us better and better approximations. So let's start with some notation. We're going to break this up into 4 rectangles, sort of arbitrarily. I'm going to do it for demonstration purposes. Here, even better. Let's do it like this. Ooh. Hopefully that glare isn't too bad, because I think that this is going to be cool. We're going to start by breaking it up into 4 rectangles. 1.5 at 2 at 2.5. And the question is, how tall do you want your rectangle to be? And we're going to start by using the right side of the rectangle is going to be the height of each of these rectangles. So the height at 2 is up here at 4, the height at 2.5, and then the height at 3 is all the way up at 3 squared, which is 9. So I broke up the interval that we're considering into 4 equally sized pieces, and I let each of these rectangles be a height that's given by the functional value of the right endpoint. The notation for that is r sub 4. R because I'm using the right endpoint of each little interval, and 4 because I broke it up into 4 different rectangles. And I'm going to approximate the area under the curve by finding the area of these 4 rectangles. And you can see clearly the area of these 4 rectangles is going to be too big, because these rectangles are taller than what the curve is. But again, this is just an approximation, and we'll see why this is helpful in just a second. So move this up. Does that help the glare? No, the glare stays still. Oops. There we go. So what is this sum? So the area of this first rectangle is going to be the width of the base times the height. And the base is always going to be equal to 1.5 minus 1, which is 0.5. And the height is going to be the right endpoint plugged into my function. And in this case, my function f of x is equal to x squared. So that means I get 1.5 squared. So this 0.5 is the width of my first rectangle, and the 1.5 squared is the height. And that's just for the first rectangle, right? And we need to do this 4 times. So my next rectangle also has a base that's width 1/2, and it has a height of 2 squared. My next rectangle has a base of 1/2 again, and a height of 2.5 squared. I'm plugging in the right endpoint into my function. And then finally, I have a base of 0.5 and a height of 3 squared. And if I wanted to, I could calculate all this out in my head. 1.5 squared is what? 2.25, and half of that is 1.25. Instead of doing all that work, I've actually, maybe I'll write that out. So this is 1.125 is the first rectangle's area, and then 4 divided by 2 is the second rectangle, and then the third rectangle is 3.125, and then the final rectangle is 9 divided by 2, which is 4.5. And so that means using our right rectangle sums, I get that the area of these rectangles is equal to 10.75, which we know is bigger than the area that's just under the curve. But we're going to do this a second time. And the second time, we're instead going to look at the left endpoints. So the notation follows really similarly, right? Let's redraw our picture. So again, we're going to break it up into 4 equally spaced intervals at 1, 1.5, 2, 2.5, and 3. But instead of taking the right endpoint as the height of each of these rectangles, I'm going to take the left endpoint as the height. So this first rectangle is going to have the left endpoint is 1, and 1 squared is a height of 1. Similarly, this next rectangle is only going to go up until the left endpoint hits the curve. And we can see from this picture that this is clearly an underestimate of the area, because all of these rectangles are underneath the curve, that these triangular-ish sections are sections that aren't being accounted for in this summation. What is this summation? So this one, the notation is similar. L sub 4, L because we're using the left endpoints, and 4 because we broke up the interval into 4 different rectangles. L sub 4 is given by 1/2 of the left endpoint squared, which is 1 squared, plus 1/2, again 1/2 is the base, and the height is 1.5 squared, plus 1/2 times 2 squared. And then our final rectangle is the rectangle that has a base of 1/2 and a height of 2.5 squared. And if I sum all of these things together, I end up with my left sum being equal to 6.75. So that's my L4. Now recall that we saw that our R4, our right sum, is equal to 10.75. I can even, the graph, I can overlay the two. This looks messy, but you see that the right ones are way too big, the left ones are way too small, and so, of course, just like Goldilocks and the Three Bears, we have one other way to be able to measure this, and this is using the midpoint. So for our final summation, I'm again going to break it up into 4 different rectangles. So this is 1.5 and 2.5. But instead of using the right-hand endpoint or the left-hand endpoint, I'm actually going to use the height of the middle value of the rectangle. So the middle value is 1.25. So I'm going to go until I get to that functional value and make the height of my rectangle look like this. And then my next midpoint here is 1.75. And then my next one is 2.25, and then my next midpoint, my final midpoint is 2.75. And these give me rectangles that are going to be more accurate than the previous ones, but it's still an approximation, right? So let's go ahead and compute. This is called M4, M for midpoint, 4 rectangles. And the computation is the same. Just like the previous rectangles, I'm breaking this interval up into 4 equal pieces, so each piece is going to have a base of 1/2. And the height in each case is the middle point plugged into my function. So 1.25 squared plus 1/2 of 1.75 squared plus 1/2 of 2.25 squared plus 1/2 of 2.75 squared. And when I compute all of that out, I end up with a value of 8.625. That's my midpoint summation. So these are 3 different approximations, and we know that our left endpoint was an underestimate. Here's my left endpoint picture. Our right was an overestimate, and our midpoint is somewhere in between. And it turns out that I can look at this picture and I can guess that the midpoint is still a little bit of an underestimate. And that's because the area, like if I just look at this rectangle right here, it's not accounting for this much area and it's over counting for this much. And this is going to be a bigger value than this. But those are subtle details. This is the basic tool that we're going to use to be able to approximate areas. The next question that you might ask is, why did I choose to do 4 rectangles? And I did it for the demonstration in this case, but as I choose more and more rectangles, this approximation is going to get closer and closer to the actual area. And that's what we're going to see using a little bit of technology in the next video.